This is our patented Institute of Making slipometer. And if I crank this lever, we should see the effect friction will have on these materials.
Different materials have different coefficients of friction. The smoother these blocks of wood are, the less friction they'll generate and the more easily they'll move.
Yes.
No matter how smooth you make the wheels and the tracks, they are still in contact with each other. There will always be friction, and that works against the efficiency of the train.
But the challenge for transport would be really to eliminate friction altogether. And at the moment, we do that with magnets.
We've been trying to use magnets in transport since the 1940s. Engineers have worked out that by creating a magnetic field beneath the carriages using magnets, they can repel the track underneath it, effectively levitating the train. Electric motors can then propel it at much greater speeds. The journey from London to Edinburgh could be completed in under an hour, 5 times faster than it can be done today. These trains are known as hyperloops and could be used here within the next 10 years. But producing a large magnetic field to lift something so big requires a heck of a lot of energy, and it costs a lot. So the dream is to find a way to achieve the same effect in a much more efficient way.
But scientists are working on an entirely new class of material that will be able to do this at much lower power, but still levitate a train. They're called superconductors. And I have one here. This is a yttrium-barium copper oxide superconducting ceramic.
This particular superconductor is incredibly good at repelling magnetic fields and needs much less energy to do so.
So, this setup is superconductor, little polystyrene carriage.
It's sitting on a track made of magnets, which is what we want to repel, and it should be capable of levitating above the track.
But only when incredibly cold, and in this case, minus 196 degrees Celsius via the use of liquid nitrogen. Here we go. Now, it looks like it's boiling, and essentially it is, because in comparison with the liquid nitrogen, this is very, very hot. So we're cooling it down, We need to keep topping it up for it to get down to temperature. Right, let's see. It's levitating! Wow. Now, that is a levitating superconductor. So delicate and poised with just this tiny cushion of air, but that air cushion is thick and strong. It's not like a standard magnetic field where you feel a push and a pull. This is locked in into a kind of chubby airspace. I'm going to push it a bit.
The superconductor is acting in a similar way to the hyperloop. It's using magnetic levitation, but holding the train in place without electricity.
But the problem is, when this warms up, this superconducting effect will stop and it will just fall back onto the track. So this will last as long as we can keep it cool, and it takes a lot of energy to keep this material cool.
Engineers in China have come closest. Their maglev train levitates with superconductors using liquid nitrogen to keep the temperature super cool. But just like powering the hyperloop, this is incredibly expensive.
So right now, this isn't going to provide us with a solution for frictionless travel. But if we can get these superconductors to work at room temperature, then we're onto something.
But you're always being limited to wherever there is track. So to really travel at speed, you need to take to the air. And the latest innovation for improving travel in the sky involves coatings. Coatings can be used to change the properties of a material, so you can improve the job it does or make it do something entirely new.
It's possible to turn a material like this into something entirely hydrophobic, that is therefore afraid of water and does not absorb it at all. So the same paper towel, this time coated with a nanoscale hydrophobic coating, and you'll see the difference. And this time the water just runs straight off, totally dry. I can even blow the water off it. Let's try some red wine. Plenty of stainage.
This hydrophobic coating uses microscopic pieces of glass to change the properties and performance of the paper. Aerospace companies are looking to ceramic coatings to change the performance of key components in their engines.
On average, a jet plane produces 24 tonnes of CO2 for every 1,000 miles, which is a lot. So engine manufacturers need to develop new materials to make air travel more efficient, but also less harmful to the environment.
A modern jet engine generates temperatures of around 2,000 degrees centigrade. That's higher than the melting point of most of the materials it's made of. One of the people responsible for working out how to stop these key components from melting is Chief Engineer Andy Gear.
Andy, hi, I'm Zoe.
Hello.
Thanks for having me. Wow, so this is a jet turbine engine.
That's a jet turbine engine.
It's tiny. What means that this doesn't just melt then?
So we keep the metal cold, or cool air, by blowing cooling air through holes in the metal blade.
This flow of air reduces the temperature at the surface of the blades to 1,400 degrees centigrade. But Rolls-Royce have developed a coating that can bring it down even further, to just 1,150 degrees.
This is a more modern blade.
Oh, it's much smoother.
The white coating is a ceramic designed to insulate the metal from that hot gas.
So this is an insulative coating.
Yeah.
That means this can operate even more efficiently.
It's a significant contributor to making engines a lot more efficient.
It's really impressive.
But the best way to increase efficiency would be to reduce the overall weight of the engine. And ceramics are playing a key role here too.
So we stood in front of one of our advanced research engines that allows us to challenge getting rid of some of the metallics in the engine. Here's an example of a nickel superalloy seal segment.
Okay, so that's a standard part.
Today's technology, if you like.
It's quite heavy, actually.
Pretty heavy.
Yeah.
Now we replace it with something like this. You can feel how much lighter that is.
That's incredibly light. I mean, it's like holding a piece of lead and some balsa wood. I mean, it's really starkly different.
Much lighter.
Hang on, I need to have a... This is this woven?
Yes,
woven ceramic?
It's a woven ceramic.
Engineers weave silicon carbide fibres together, then fire them in a kiln, just as you would with most other types of ceramic.
Oh my God.
Hard wearing, very high temperature, doesn't need air cooling.
So when you make it out of ceramic, you don't need to cool it?
That's right.
And the implications of it being this light are that it could therefore make a much more efficient engine?
Yeah, every pound of weight you can take out of the engine is a pound less you have to lift off the ground. So you need just a whole lot less energy, therefore a lot less fuel burn to get the aircraft airborne.
This is extraordinary. I have never seen anything like this. It's actually quite an alien object. It really feels very futuristic.
Material of the future.
One sector that's forever striving to innovate is medicine. And once again, developments in materials are right at the forefront, not just in our hospitals and operating theatres, but inside our very bodies. Dentistry accounts for around £3.4 billion of the NHS budget in England, much of it spent on replacing damaged teeth with implants and crowns. But having one fitted is no guarantee it will last.
This is zirconia, a ceramic material which occurs naturally as a mineral called baddelite. And this is the stuff that they fire in a kiln and turn into solid blocks like this. And then these blocks are machined to create crowns, fake teeth. This is one that's been machined. There's the little toothy peg there. And here it is as a crown, which is great. It's hard, relatively long-lasting, but it doesn't last a lifetime. And that's a problem. It will need to be replaced.
These crowns have a tightly packed structure of micron-sized grains of zirconia, smaller in diameter than a human hair. That might sound tiny, but moisture can still get in between the gaps.
Because the mouth is actually a hostile environment. There's lots of acids, but also just the moisture alone causes something called hydrothermal aging, which essentially causes the ceramic to wear out.
If we could reduce the size of the grain structure, the material would become more hard-wearing. To demonstrate, I've got some sugar in two different forms. The cube represents a modern zirconia implant. The clear block is a tougher, denser form of sugar.
We've got a granulated sugar cube and then a solid lump of sugar here. And when I dip them into the water,
as you'd expect, the sugar cube starts to fall apart. There are more gaps in its surface, so moisture can get in. And this is how, over time, hydrothermal aging affects a standard zirconia crown. But for the solid chunk of sugar, it's a different story.
this one has a much finer structure and is hardly damaged at all. So the challenge for dentists is to make a crown that's immune from hydrothermal aging.
And scientists at the University of Loughborough think they have the answer. Professor Balavedi Anathan has created an amazing new process. Instead of using the standard micron-sized particles, for the first time, he's using nano-sized zirconia, which creates a structure where the gaps are too small for moisture to penetrate.
Zoe, that remarkable hydrothermal aging resistance is because of this wonderfully fine-grained nanostructure.
This is the current state of the art. It's extraordinary. We've been able to go from that just down to that.
And that is what gave us a final product, which is an everlasting teeth, which has complete immunity towards hydrothermal aging.
So it's this tiny grain structure that gives it that everlasting quality.
That's right.
The new nano-sized particles of zirconia create a much more durable structure because they are so unimaginably small. And because they are so fine, they can fit through the nozzle of a high-resolution 3D printer, meaning new teeth can be printed to order.
So now I'll show you how we manufacture a dental implant using 3D printing. So this is Yumeng. She's doing a PhD with me.
So you've already printed two, they're perfect little molars.
Absolutely, yeah.
You're actually looking at the molar, which we scan the files from the real patient, and then we put that into the software and tell the computers what to do for the printer.
It just takes 20 minutes to print a molar.
And it's very shiny. So this is the syringe here. So you have your material loaded in there.
Absolutely.
And then, like an icing bag, it extrudes it out.
Yeah.
Out of this tiny, tiny
Absolutely.
nozzle.
It's called micro extrusion. This nozzle is really of the very small size.
The paste itself, is that, how
Actually-
liquid is it? Ooh. Ooh, that's nice. It's actually a consistency very similar to face cream.
Yeah.
A little bit sticky as well.
Yeah, it has to have the thickness to hold the shape.
To solidify it, the tooth is fired for an hour in a microwave kiln. This rapid heating locks the nanostructure into the final shape, meaning the tooth can't break down.
Our tooth, like this one, has gone into the oven.
Yep.
And whereas this is how it's going to come out when it is fully dense.
Ooh, it's shrunk quite a lot. And how much has that shrunk by?
It's probably by 40%.
Yeah.
Yep.
Yeah. So it is the very fact that you've printed a powder with a small grain size and then used a microwave kiln to fire it that gives this property of being able to resist
Absolutely.
hydrothermal
It's the
aging.
material and the process, the combination together to achieve a product which will be completely immune to hydrothermal aging.
So that is our everlasting tooth.
These wonderful, everlasting crowns are now ready for use, meaning the need for expensive replacements could become a thing of the